Question 3. The kinetic theory of gases can also be applied to the free electrons in metals, just as though they were atoms in a gas. Use the equation 3/2 kT equals half m c squared bar to estimate the root mean square speed of nitrogen molecules at room temperature. So if I rearrange this equation, I get c squared bar is equal to 3 kT over m. But I want the root mean square speed. So I'm going to put a square root over both sides. And so now I know what I want to do. The square root of 3 times 1.38 times 10 to the minus 23 times room temperature. So if we take it to be 20, that would be 293. You might have chosen a slightly different value, but 20 is fairly standard. Divided by 9, and the mass of the hydrogen molecule I want, don't I? Which is, so we knew what the molar mass was, didn't we, from the previous question, 0.028 kilograms divided by the number of molecules in a mole. There we are. These 3. So we need to take the square root of that, which gives us 508. So we're probably going to write 510 meters per second. That's the nitrogen molecules. And then the second part says, what's the root mean square speed of free electrons at room temperature? So we're going to use the same principle. The square root of c squared bar, the root mean square speed, is the square root of 3 kT over m. So everything on top is the same. The square root of 3 times 1.38 times 10 to the minus 23 times 293 divided by, then we want the mass of an electron on the bottom, so that's 9.1 times 10 to the minus 31 kilograms, which gives us a speed of 115,000 meters per second. B. The energy levels of electrons in a metal are a few electron volts apart. Show that 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. So here we're using the energy equation E equals QV, but the charge that we're using is the charge on 1 electron. So this is 1.6 times 10 to the minus 19 coulombs times 1 volt, which just gives us 1.6 times 10 to the minus 19 joules. That's where the electron volt comes from. So energy when an electron is accelerated through a potential difference of 1 volt. Calculate the kinetic energy of an electron at room temperature in electron volts. So we'd normally say that we're working in joules, and we'd have half m c squared bar is equal to 3/2 kT. So if I do it like this, 3/2 times 1.38 times 10 to the minus 23 times 293, that gets me it in joules. So to convert it into electron volts, I then need to multiply this. I'm going to put this in square brackets because it's converting the unit at the end. 1.6 times 10 to the minus 19 to turn it into electron volts. So that gives me a value of 0.038 electron volts. Not times, divide. So I've done that wrong, haven't I? Let's correct that. So to turn the energy into, so it was a small number, therefore I had to divide by that to make it a bigger number. Sorry. Explain whether the electrons in a metal at room temperature have enough energy to cause excitations of the ions in the metal. So it told us up here that the energy levels are a few electron volts apart. So no, they cannot. The energy level jumps are much bigger than the electron energies, which is good news, because otherwise we'd be having the atoms in the metal getting excited all the time by the electrons. Describe qualitatively what happens when a free electron collides elastically head-on with a stationary ion in the metal. In your account, explain the role of the law of conservation of momentum and energy in the collision. You may like to draw a diagram showing the electron and ion before and after the collision. Sure, so we've got a positive ion and a negative electron. This is going to approach at speed v. Because it's an elastic collision, afterwards you're going to have an electron moving away, still going at speed v, but in the opposite direction. So the kinetic energy before and after are the same. The law of conservation of momentum implies the ion should move back, but the mass of the electron is much smaller than the mass of the ion. So we could say ion speed is negligible. So we tend to show them just as being stationary. In a real system, they're going to be being bumped into from all sides rather than just one side. So we'd expect it to cancel out anyway. D, describe qualitatively what happens to the free electrons in a metal when an electric field is applied by connecting a battery across the wire. So if we could imagine our metal as being like a container of gas, we've got all of our negative electrons. We're going to have positive charge connected from one side of the cell, negative from the other. And so all of our electrons in here are still bouncing around like the gas particles that we were imagining them to be. But the whole time they're bouncing around, they're experiencing a force acting in this direction. Now, the force is relatively small. So in terms of the paths I've drawn, I might just show that maybe they're going to follow a path that takes them slightly more in this direction than they had originally. So not a huge difference for this one going over here. So they experience a force to the left in my diagram, a force towards positive. And the term we use is the drift velocity, isn't it? So we're going to say they drift in my diagram to the left. But we'd still have plenty moving to the right. It's just overall they have this bit of force pushing them to the left in my diagram.